Good evening, everyone, and welcome to this ground improvement 6th class. My name is Rajat Bonik, and I am one of the PMRF fellow at IITISM Dhanbad, and I am get opportunity to take this ground improvement discussion class, uh, which is conducted by Nptel and also taught by Professor Dilip Kumar Vaidya sir, well-known person uh, in at IIT Kharagpur, uh, and I am one of his TA in this session. And today is six of this ground improvement discussion class. And in this session, I will discuss about this week six five about this week six classes, around five classes, one by one, and which is including theory, also including some maths or problem. And then I also discuss some, if time permits, I also discuss previous year assignment problem regarding this NPTEL class. And I also try to solve some problem in this week regarding this week problems theory. So let's start our session, and then and also I want to wish everyone a happy Raksha Bandhan, uh, and also I want to inform you that we successfully launched the Aditya rover, Aditya rocket for uh, discovering or the sun. So it is great achievement for our India. And now we will start our session. I will share in few minutes. I will share my PPT. Please be patient. Uh, I am sharing my screen. Please wait. I think uh, my screen is visible to everyone. And please wait few minutes. I think it is visible to everyone. So let's start our session. In this previous week, we talked about the different about the ground improvement introduction about the ground improvement, different ground improvement techniques. Then we discuss about the shallow compaction, then deep dynamic compaction, then discuss about the vibro compaction, and then vibro replacement. In last week, we discussed about the vibro replacement technique. And today, in this week, we discuss another ground improvement technique, that is deep drainage and dewatering. So we know that water is life for our living purpose, but in case of construction purpose, it is vulnerable to our construction or handling the construction. It may cause damages or reduce strength, or it may cause some uh, corrosion to the structure. So we need to handle this water during the construction. For this reason, we introduce two ground improvement technique. One is drainage, another one is dewatering. Both are similar, that both are used to address the water during the construction, uh, but there is few uh, relative changes or few difference in between these techniques. One is drainage and another one is deodorant. So let's start from the slide one. Here it is said that Water is the most common use for failure of geotechnical engineering, and detrimental effect of water on the soil are. And this there are different causes, reasons which is have detrimental effect to this structure. One is due to water. One is reduction of strength and stiffness. Another one is increase of weight and generation of excess pore water pressure, necessary condition for liquefaction, development of uplift force, development of seepage force, increase of lateral earth pressure, expansion, collapse, erosion of soil particles and rock, migration of fines, freeze, thaw, stripping of asphalt pavement. So reduction of strength in the sense, reduce strength and stiffness in the sense means if the groundwater table, that means below the ground surface, the groundwater table is very close to the ground surface, then there may be increase of pore water pressure. Due to this pore water pressure, effective stress is reduced. And we know that effective stress is a function of shear strength. We know the shear strength is a function of effective strength. So reduce or indirectly reduce the shear strength, and due to the reduce of the shear strength, the water, if the structure, if any structure is present in the soil or in condition, that may be failure due to the bearing, or there may be shear strength. So that one cause, the one reason we address the water. Another is increase the weight in the sense, in case of slope failure, we know that during the rainy season, in the hilly areas there may be huge amount of slopes are fails, and or we can say landslides are happen. The reason is, in these landslides are, if due to rain the water are fully saturated, and due to this water, and water has also some weight, and increase the weight of the soil or weight of the slope, and after increase the weight of the slope, the resisting force is less than, or we can say the uh, uh, force which is driven force, driving force is greater than the resisting force, and that reason the slope is failed and landslide is occur. And we also know that due to this water, excess pore water is developed, and due to this excess pore water pressure, shear strength may get reduced, or we can say effective stress may get zero in portionless soil, and liquefaction phenomena can happen. And also, due to this water, uplift force or seepage force is created. Uh, i- in these two cases, uplift force and seepage force is happening in dam purposes. If we can say one dam is here is present, and one side is higher water table and another side is lower water table, there is some head difference is created. Due to this difference, water, we know that water flow from higher head to lower head. So water can pass like that. So there may be, during this passage of water, there may be in soil there may be seepage forces developed, or also if water like that, there may be uplift force also may develop. Due to this uplift force, seepage force, sometimes foundation of the structure may fail if the uplift force is greater than the foundation weight. And another other aspect is that increase of lateral earth pressure. We know that if there is a retaining wall is here, and there is some backfill material in dry cohesionless soil, we know that most of the cases the backfill material is cohesionless soil, and if the water is present or groundwater is high to this backfill material, there may be excess weight is created. This is weight or hydrostasis force, we can say hydrostasis force is created like that. This hydrostasis force may create extra force on the retaining wall, and due to that, lateral earth pressure is increased, and slope, retaining wall may be failed. And also due to this water, expansion and collapse may be happen. Expansion in the sense there is some soil which is very sensitive to water, like bentonite clay or like many of the clays or particles. In this case, clay and seal, it is very sensitive to the water. If water is present there, that soil particles maybe absorb this water and soiling can be happen or expansion can be happen, and this may cause the detrimental effect to the structure if there is any foundation is present in this soil. So also there are some soil which is very sensitive. If in normal condition they possess good strength, but in little bit disturb some like water or air, they may be suddenly collapse, and that may affect our huge damage. So this can happen also due to this presence of water. Also, erosion of soil particle and rock happens, and migration files also happen due to the seepage forces. Freeze and thaw also happen. That means in polar region or we can say uh, cold weather or winter season, there may be happen if the we know that if water temperature falls below the 0 degree, water may converts to ice, and due to this ice, water get expand, and during summer season, this ice melted out, and again it is gain its origination due to this expansion and reduction construction. The structure of soil may be damaged. That may happen due to presence of water also. And another also the stripping of asphalt pavement. We know that due to rainy season there is high force of water is in the pavement, and due to this pavement or infiltration of water in pavement, there are some damage of pavement particles or pavement surface, and that may cause, if proper damage is not there, that may cause the detrimental effect to the pavement. These are the many reasons, few reasons which is caused by the presence of water in most of the case. So in the next slide, we discuss what is the remedies in next few slides. And here one point is clear that written that the majority of the problems can be solved if water is removed from the soil, pavement, or any earth structure. Managing surface water by providing appropriate slope can be easiest solution for many problems. Here it is said that water cause the detrimental effect. We know that we discussed recently now. But we can address this water, or we can say surface water, by providing appropriate slope during in the first case. This slope may be given for different structure, like that for pavement. This slope may be in between 1.5 to 4%. As for shoulder, this slope may be 4 to 6%, and for ditches, this may be 25 to 50%. But this removes water only up to few percentage in our construction site. But for deal with the major problem or majority of the problem, we need some other techniques to introduce to reduce the water from the or to remove the water from the construction site. So here one figure is given, or this techniques are, we can say these techniques are to control the groundwater, or given as drainage, dewatering, or barrier. So here it is said the management of surface is not well, we know, and there are some other techniques and methods, that is drainage, dewatering, barrier. So here diagrams are given. In next to slide, we see that first is given for drainage, and second is for dewatering, and third is for barrier. So here we can see that one for drainage, one retaining wall is given here, and after that one drainage material is incorporated here. This drainage material is nothing but gravel, or we can say coarsenless soil or gravel, a coarser sand or gravel, and one geomaterial also given to as a filter to resist the backfill material to flow out from the retaining wall. So we can see that for here one drainage material, or you can say gravel material is here is incorporated, and then one filter material like geosynthesis material is applied here to filter the water, only pass the water like that. If you clearly, I can say like that, this filter is given, so only pass the water only, and all the water is collected here, and through a pipe this water is removed from this retaining wall, so no excess pressure is developed in the backfill material in retaining wall, and retaining wall the life of the retaining wall may be increased to by this arrangement. This technique is nothing but called drainage technique. And another one is the second one is called dewatering technique. In this uh, technique, we can say that here the original water table is here, but we need to excavate up to here. If we excavate without the dewatering, the water may uh, get into this excavation base, so that may causes many detrimental effect to our construction, or may cause some problem in our construction. For this we need to dewater by some arrangement. Here it is, here one of the arrangement is, here it is oil point, by oil point. So in this we can in oil point system we introduce one pump at the top, and we duct or we inserted a long pipe into the ground, and after that due to the this arrangement we suck out, or we extract out the water from the ground surface. Due to this the original groundwater level may be reduced like that way, due to the influence of this or power of this oil point. So like that, after the dewatering, the sorry, I can after the dewatering, the water table may come to that level. You can, if you see my skin, I draw that one water table here. You see that the water table may comes to that level. So there is no problem to this excavation. So we can start our construction, no problem to any detrimental effect here. So like that, there is one technique. It is called dewatering technique. Another one is barrier technique. Barrier technique mostly used in pavement road. So if you see that in barrier means we block the water to come out into the uh, come into the pavement sub base course like that. For that, one barrier wall is created on both the sides of the pavement. This wall may be backfilled with a good drainage material like gravel or sand soil, and also some filter material is around incorporated around this barrier to pass only water only, to pass water only. Okay, so this barrier wall may block the water which is coming outside the pavement, and due to this barrier wall, the water get into this wall barrier, and after this we know that gravel is a good drainage material, and then we collect the water here, and we can remove by some other arrangement or longitudinal drain or some transverse drain, that water may be extract out from this, and no water can be incorporated or into this pavement region. And due to this arrangement, the pavement surface may be safe from this water during rainy season. So these are the three techniques used in to handling water in this construction site. So coming to the next slide, we will discuss one by one these techniques. So in this week 6, the majority of our discussion is regarding to the dewatering technique. But we discuss about some other techniques like drainage or barrier in few slides. So first one is drainage technique. Here it is said the basic concept is the drainage technique is removal of water which can prevent the damage and failure and maintain performance and prolong life of this structure. The highly permeable granular geosynthetics on combined layer, sometimes called drain, can be installed to remove the water from the roadways, earth structure, ground, as we already discussed. And drains are often protected by filter or have a filter as a part of the drain to maintain their long-term effectiveness. So we use the drain with the filter arrangement so that the drain can work in a long term effect or in the long run, and effectiveness may be maintained this drain. So main purpose of the drainage is removal of water by some arrangement, and here it is used some granular material, or we know the granular like gravel or something, or some geosynthetic material, or both of them. So first here one picture is given as granular drain. So if you see that one granular drain is built at the left side in the figure. So this drain, main purpose of this drain is to collect from the water outside the pavement or from the pavement and drain out by a pipe or some other arrangement from this pavement, and this pavement structure may be saved from this water. So another one is geosynthetic drain. Without uh, uh, if we apply geosynthetic drain in place of granular drain, that may be called geosynthetic uh, drain, or you can say. So you can see that here it is one pavement is drawn, a pavement surface is present, and one drainage material or geocomposite are present at the below of the pavement. This material is collect water like that from the pavement like that and drain out by a simple slope arrangement by this original longitudinal drain. So this is one of the arrangement. Another one is combined drain. Combined drain in the sense which we use both textile or geosynthetic material and gravel or granular material. So if you see that here in the below the ground surface, one arrangement is created like one geosynthetic material is inserted and below into and insert uh, in this geosynthetic material some good drainage material like granular material or gravel material is placed, which can address the strength also, and also a good drainage also, address the good drainage also to remove the water. So this is another arrangement. So coming to the next slide, here it is said that there are four types of drains we can use in our practice. Uh, one is sorry, uh, drainage layer or blanket. Another one is longitudinal drain. Another one is transverse drain, and last one is vertical drain. So drainage layer or blanket, nothing but it is called the geosynthetic drainage. Okay, and if you see, you can see the previous figure V. One layer is incorporated below the pavement surface. This is nothing but drainage layer, and this drainage layer, most of the case, it is made of geosynthetic material. So this is one type of drain. Second one is longitudinal and third one is transverse drain. Longitudinal in the sense it is throughout the length of the pavement. This drain is incorporated. As transverse drain is at the cross section or at the cross of the pavement, one drainage or in at the different junction, one at the transverse direction of the pavement, one drainage incorporated to collect the water. The fourth one is vertical drain, which is very good to uh, uh, good to reduce or the water from the or excavate or can say dissipate the water from the ground surface some great depth. And this drain is sometimes used uh, in the consideration purpose. That means in consideration, if preload is here and due to this preload, excess pore water pressure is developed below this surface, and if we this excess pore water pressure, if we remove this excess pore water pressure from the surface by some arrangement, one of the best arrangement is vertical drain, and due to this vertical drain, water get collected from here and here, and by some another arrangement, this from this vertical drain, water can remove and expel out, and excess pore water pressure is reduced. And due to this excess pore reduced, effective stress is increased, and ground settle and increase the shear strength of the soil. So this vertical drain is used for this reason only. So here it is said the granular drain. Drainable pipes are often included to collect and discharge water. Vertical drains are often used in the ground to dissipate the excess pore water pressure. We already discussed that, induced by the dynamic load, or we can say the preload, or such as deep dynamic compaction or preloading. Okay, so here some example is given in some other arrangement we can say given for drain out the water. So first one is trench drain, second one is pavement drain, fourth one is retaining wall drain, and third one is retaining wall drain, fourth one is chimney drain for dam only. So trench drain is nothing but one trench is created like that. After that, some combined draining system we already discussed like geosynthetic material for filtering the water, and some inside that some good drainage material like uh, gravel or granulous soil is incorporated, and after that by this arrangement water can collect it from surrounding soil and drain out this from this region. In pavement drain, one same layer is incorporated below the pavement to collect the water from the surface like that. By this arrangement water can easily uh, remove from the pavement surface. Another one is retaining wall drain. You can see that the backfill material in the back of the retaining wall, one good drainage material like granular soil or porous sand or gravel material is placed here, and surrounding that one geosynthetic material is incorporated to only filter out only water, and by that one pipe arrangement like that is happening, and if there is excess pour or excess water is present, this water is drained out this system and through this pipe, and this background material is safe from this water. Another one is chimney drain or for dam or leaf. So in chimney drain, if you can see that it is applying dam. So like that one drainage material or we can say geosynthetic material is applied. By this geosynthetic material, like that only, this arrangement is happening. So if water is entered to that, this this surface is impermeable surface, but this first surface is permeable. So water can get into that, and by this way, it is expel out from this uh, arrangement and save the structure. Another one is inceptor drain or toe drain. So this inceptor drain is toe drain is applied on the slope surface or at the toe of the slope. What happens if there is in rainy season, the running water is coming from the up hill, which is gradually increase its velocity. Due to this, the slope may be failure by this velocity, and because by this velocity force is developed and slope may be failed. So to reduce this force, one at the toe, one drainage like trench drain, we already discussed trench drain. One drainage arrangement is happening to intercept this water to come to the downstream. So the water from the hill is coming out like that, and by this intercepted drain, this water is collected from it, and through a pipe arrangement, water can be removed from this source. So we already discussed the vertical drain in this previous slide. Here one pictorial arrangement is given like that. This is a ground surface, and here it is some soft clay is present, which is very soft in strength wise, and one to strengthen the soil, one arrangement is happened to consolidate the soil. One is preloads is given. Due to this preload, excess water pressure is developed, and by this arrangement of vertical drains, this water excess water is collected, and through the surface piping, this water can be dissipated from this soil, and consolidation happen. And due to this consolidation, subsequent ground settlement is happen. After that, soil effective stress is increased, or soil gets stronger. So here some discuss about the disadvantages of the drainage technique. So it is said that drains are easy and often inexpensive to install. You already know this. No expensive material is used. Only some gravel, good drainage material, or some geosynthetic material which is already present in low cost to create one drainage environment. So they are effective to minimize or prevent our water related geotechnical problem. They are used, and they are discussed some advantages regarding this drainage. It is said that it is reduce the water soil moisture content, increase soil strength, and increase soil modulus. So soil moisture content in the sense water can remove, so easily soil moisture content is reduced. If water reduce, then effective stress is increased, and automatically soil strength also increase. Due to the increase of soil strength, soil modulus also increase. That is K. Soil modulus, young modulus, also we can say also increase. Also, it accelerate the consolidation and settlement. We know that, or we also discussed that due to the vertical drainage, that we water during the consolidation water easily dissipated sorry excess water pressure can easily dissipated through this vertical drain, so it is accelerate our consolidation and settlements is happening. Also reduce the lateral earth pressure. If we know that due to some arrangement, the water is backfill, water can collect it from the backfill material, and this backfill material gets dry, and the pressure, hydrostatic pressure is reduced from this backfill material, and due to this, lateral earth pressure also reduces, and the retaining was also safe. It also reduces the uplift force. We know that if the water is present here, some uplift force or buoyancy force is applied at the below the foundation surface. If we remove this water, the uh, active force is reduces and the foundation gets stable. Also, the rate of pavement deterioration. We see the previous pictures. There is in below the pavement there is one drainage is present, and due to by this arrangement, this water get collected and pavement strength is increased. And there is other is minimize the soil expansion, minimize the soil collapse, minimize the forced and heat action, throw action, and enhance the stability of dams, leaves, and slope. All the cases we already discussed in our previous slide. So, so there are some limitation also in drainage technique. It is said that vertical drains in soft soil effective only if there is surcharge or excess pore water pressure induced by dynamic load. So we know that or we see that in our arrangement. If the preloads are present, there after that only the excess pore water pressure is developed. And this excess pore water always try to escape or try to stable due to this stabilization escape from the soil, and this may get help from the vertical drain. But if we not apply any if not apply any preloads, there is no excess pore water pressure is developed. So this vertical drain, no use of this vertical drain. So for that, always to use of vertical drain, always there is some surcharge or excess pore water dynamic loading should be present. Also, drains cannot be used to solve the non-water related geotechnical problem. We know that the drain is also used to collect water. There is no other use of this drain. So there is no not related to solve the other geotechnical problems. The last one is it is said the limitation is said that drains may be ineffective if there are clogged. Clogged in the sense the debris or like other materials is stuck the drain, and the flow of water in the drain is maybe get obstructed. So the effectiveness of the drains may be reduces by that arrangement. So to reduce this clog, we apply the filter material around the drain, like geosynthetic material or like other material, to pass only water into the drain. So there is one advantage also to if there is clog, so drain may be ineffective. So now we can start another ground improvement technique related to the water. And, remove the water is dewatering technique. So it is said that for construction excavation or permanent structure that are below the water table and are not waterproof or are waterproof but not are designed to resist the hydrostatic pressure. So for that reason, we apply the dewatering technique. That means if the water table is present below the structure, or also if the structure is not waterproof, and another case also waterproof but do not resist the hydrostatic pressure, for that case we use the dewatering technique. So nothing but we did dewatering technique. It means we collect uh, the water from the ground, and this ground through a pipe or pump system, and this water can by this arrangement we lowering the groundwater table. So automatically the excess water pressure pore water pressure of the ground surface is reduced. Effective stress is increased. Automatically the strength of the soil also increases. So here in two ways we can dewater in this dewater the soil. One is permanent way, another one is temporary way. But permanent way we apply in less areas or only apply for high valuable construction or high construction sector only. But temporary construction is applied or dewatering technique is applied in most of the cases to address or to deal with the water or to remove the water. So here also like drainage technique, here also dewatering also happen and uh, in different types or different ways. So first one is some trenches and pumps arrangement. Like that way, we also dewater from the ground. Another one is well points. Third one is deep wells with submersible pumps. And last one is electroosmosis. So one by one, we discuss these techniques. So first one is sumps, trench, and pumps techniques. These are used to handle the minor amount of water only. Like only in the groundwater handle the water like only if the from the ground surface below like 1.5 meter or less. So the height of the groundwater above the excavation bottom is relatively small, 1.5 meter or less, or surrounding soil is relatively impermeable, such as clay soil. For that only this technique is used. That means if the surrounding soil is impermeable, there is no further infiltration of water happening. So this technique is easily used. That means water is collected by some trench or sumps or pumps, and by this way drain out some this water from another area or region. But this technique is little use, have little use or has little use only. So if you see this picture, this picture is on slope is given or shown here on slope. The original water table is here by some arrangement or trench or sump arrangement, pump arrangement. The water from this slope is collected and pump out to another region, another area. Like that, the original water table is reduces or draw down at that level, and this arrangement of the slope above the water after the water table after the disarrangement get safe. So you can see that there is some or strength is happening created and some skin also given to only collect only water. After that, if the water is collected, this water is drained out or pumped out by a pumping machine to another region, and by that way, the slope gets stable. So here a few points are made regarding the sumps pumps. The sump pumps are frequently used to remove the surface water and a small infiltration of groundwater. Sumps and connecting interceptor ditches should be located well outside the footing area and below the bottom of the footing so that groundwater is not allowed to disturb the foundation bearing surface. In granular soil, it is important that fine particles not to be carried away by pumping. The sumps may be lined with a filter material to prevent or minimize the loss of fines. So we already discussed this every step. The sump is only used to remove the surface water and small amount of infiltration water of the ground water. And also this is used outside the footing area or below the footing area to collect the groundwater, and this which is not affect the foundation bearing. And also if there is granular soil is used to reduce the flow out of the fine particle, filter may be used, because if there is no filter, the fine particles of the soil also get washed out. If the fine particle is washed out, after that few times there is the voids, or we can say cavity may created, and due to this cavity, the upper soil is collapsed. So that if not if it is not happen if filter paper is given. If filter or filter material is given, this filter material only pass water only. So like that, we can reduce the uh, washout of fine particles. So another technique of dewatering is well point method. In this well point method, multiple closely paced wells connected by pipes to a strong pump. Multiple lines or stage of well points are required for excavation more than 5 meters below the ground table. So if you see the picture on arrangement in here, so one well point means one pipe, riser pipe we can say, is inserted into the ground, and some arrangement is given here, like well point system means some filtering material is given, which is only connected only water, and this pipe is connected to a common pump, or you can say common pump, which is collected or suck out water from the ground. And there is this oil point is arranged uh, in a line. That means here one point like that, here also one point like that, and here also on a single line. And this oil point is for a first stage or single stage. This oil point is reduced the ground table up to 5 meters. That means if the ground water table is like that here, present here, it may be reduced up to only 5 meters. This that means this height is 5 meters only. To further reduce this groundwater, another stage, that means multi-stage, or another second stage is inserted, like here to to, or we can say here like that arrangement. First stage is here, so it is draw down or reduce the water up to that level. To further reduce, we excavate up to that. To further reduce, second stage is here. So it is further reduce the water table up to that. And again, if we want to reduce the groundwater table, again we excavate up to that, and again another stage of well point is incorporated, and furthermore we reduce our groundwater table. So, but we already discussed by this arrangement only. First is up to that much of original groundwater is here. After that, up to that much of groundwater table is lower. Second stage, furthermore, groundwater table is lower. By this, one excavated up to this, and one some well point system is incorporated here. Like that, third stage also we use. But if we need to uh, address without this groundwater table, or reduce the groundwater table without the excavating up to that much of depth, we incorporate another technique of dewatering, that is deep well deep well submersible pump technique. So here one high powerful pump is there, which is incorporated below the, here we incorporated below the this pipe. After that, one uh, a pipe is attaches to that, to this pump, and like that water get collected from here, and the original groundwater table may reduce by one arrangement only. So, but deep well have cost, require more money or more charge to use these against the oil plant. But it is very useful to lowering the groundwater table up to a larger depth. So here it is said about the deep wells that pumps are placed at the bottom, we already discussed, of the well, and water is discharged through a pipe connected to the pump and run up through a well hole to a suitable discharge point. They are more powerful than the well point. We know that because more energy is or more power is given to these deep wells and also require a wider pacing and fewer well points. If we say in oil points require 5 oil point energy require 5 well points, that 5 well points may be reduced by one if we apply deep wells. So it is cost sometimes it is cost effective, but the arrangement or use requires more huge money and also used alone or combination of oil points. So I mean to reduce the cost of the construction, sometimes oil points is used with deep wells also to reduce or to arrange the money, cost effective also. Here one arrangement is given for submersible pump or we can say deep well. If you see that one pump is inserted below the groundwater, below the surface. After that, this pump is collect water from the surrounding soil at the deep from the surrounding soil like that, like that, and only water only. By this screen, we pass only water only, and then some piping arrangement. This water is collected or discharged from the soil through a bulb or something like that. This is a submersible deep well technique. So another one technique is given here is deep wells with auxiliary vacuum system. We know that granular soil is good material for drainage. A questionless soil is good material for drainage. They do not or good material permeable material. They do not disturb the water flow when we apply the pump. But if there is some other material like silt, clay is present during the pumping, so we need extra energy or we need extra arrangement to drain out the water from this soil because we know that clay and silt are less permeable than the sand. So for that, some vacuum is created. To create the vacuum, one vacuum header is incorporated. By this vacuum header, some vacuum is created inside the pipe. Due to this vacuum, the surrounding water is filled this vacuum and stability is maintained. And after that, pumping arrangement also there. Due to this pump, water is collected from this surrounding soil, and like that, the water can expel out from this below this surface. So moving to the next slide, we have discussed about another groundwater technique. It is electroosmosis. So this electroosmosis happen through cathode and anodes by some electric gradients. That means if we apply cathode and anode, and through this cathode anode we apply the current. Due to this electric gradient or high voltage, the water is moved through anode to cathode. We know that water is flow from positive charge to negative charge. So water gets collected that anode cathode. So after that, the pumping from that after the that we collect the water by we remove the water through pumping. So like that arrangement, uh, we can remove the water from the ground through a current or electrical arrangement through electrical gradient or electric gradient. So we can see that here one arrangement is given of, of electroosmosis. You see that one plane is given here. From the top view, we can see. So we then some cathode one after that anode, and all this cathode anodes is connected to a electrical wire, and then a voltage potential created, electrical potentially created, and or we can say electric gradient is created. Due to this electric gradient, water is flow from positive to negative, and at, after this water is collected or accumulated at this cathode region, and some arrangement a piping system or water gets removed from the another region, from this region to another region. So if you see that the electrode or cathode here, one rod is inserted in the ground, and after that the due to this current, water is collected from the coming to this cathode from the surrounding soil, like that. So by this arrangement, electrolysis done in the ground. So now we will take 5 minutes break. After that, we discuss about the uh, other aspects of the dewatering and try to solve one problem also. And at last, we try to solve the previous year assignment problem also. So we now we take 5 minutes break. We will join after 5 minutes. Please don't leave the meeting. Stay on the meeting. After 5 minutes, I will join. So stay on the line. So once again, welcome to this session. Now we continue the further remaining part of this lectures, week 6 lectures. So in the coming slide, we discuss about the summary of other dewatering technique, or also some discussed dewatering technique in this session. So here we can see the first one is sums uh, and ditches. In sums, applications are collect water entering excavation or structure. There is some guidelines also. Generally, lower water table in stable gravel or all graded sandy gravel by 1.5 meter or less. That means sumps and ditches are only used for some up to 1.5 meter or less to lower the groundwater table up to 1.5 meter or less, or only for well graded sand and sandy soil. Conventional oil point, dewater soil that can drain by gravity flow. That means due to the gravity, this technique is used. Oil point techniques are it is only used for gravel and sand. Most common, most the guidelines are most commonly used. This oil point technique, conventional oil point technique is most commonly used. Drawdown limited up to 5 meter per stage, and may use multiple stage oil points for larger drawdown. Drawdown means lowering the groundwater table. So this technique is most commonly used, and for single stage we already discussed that this it is effective up to 5 meter, lowering the groundwater table up to 5 meter. For further lowering the groundwater table, multi stages, that means after one stage excavated, again another one stage incorporated, again excavated, like that way, stepwise, lowering the groundwater table. So third one is vacuum well point system. So it is used same through gravity flow only, and it is used only for low permeability soil like silt clay soil. If there is any silt and clay soil present in this ground, and we know this silt and clay is very low, have low permeability, low permeable soil. So for that reason, we use this type of vacuum well point system. So guidelines is that it accelerates the water flow. We know that we create the vacuum to stabilize us for stable condition the surrounding soil. The water is filled as vacuum, like that pumping the water, and like that we remove the water. So this technique also used up to remove the groundwater table or lowering the groundwater up to 5 meters. So next one is jet eductor well point system. It is a well-known or very expensive dewatering technique, and also uh, reduce or lowering the groundwater table with much more depth. So, in application part, it is said that dewater soil that can be drained by gravity flow, usually for large deep excavation where the large flow is required. That means when the large water flow is we need to remove from the ground surface. For that reason, jet eductor well point is used. So guidelines are given that lower water table as much as 30 meter. You can see that the previous techniques is remove only or reduce uh, oil point technique is reduced up to 5 meter. But by this technique, by single arrangement, this we can reduce or lower the groundwater table up to 30 meter. And this technique is particularly used for larger construction or projects like shaft means in the case of large diameter or uh, large diameter or oil foundation, we can say pile foundation, which is used in bridge. foundation for the and also using tunnels also. For larger project, this technique is used. And in this techniques, two header pipes and two riser pipes, and like that arrangement is given. And another one is deep well system. This is also lower the water table to a large depth. So dewater soil in deep well system, we dewater soil that can be drained by gravity flow. Here also we can use the gravity, and usually for large deep excavation where large flow is required. That means it is also required used for the large project where large water flow is removed from the ground. So install around the periphery of the excavation suitable for dewatering shaft or tunnel. So same as jet ejector. So last one is electroosmosis. We already described that electrical gradient or electric gradient is sorry is too hot here. Mm. Electrical gradient or created through some cathode anode arrangement or electric current. By that, water is flow from anode to cathode and collected from anode cathode and pump out from that region. And like that, we dewater the water, dewater from this soil. The and this technique is mostly suitable for silt clay, or silty clay or sand. Sometimes silt or sand present like that. And we already discussed that this technique is used when the hydraulic gradient, electrical hydraulic gradient is created. This technique is used. So now we discuss about the suitability of dewatering technique. So this technique you use for that there are few factors depend. This technique depend on few factors like location, type of soil, and size of the excavation, or we can say size of the construction or depth of the excavation or construction. Like what type of fire we can use, whether that region is fully saturated or not, type of soil, which type of soil is used, either portionless soil or fine or silty soil, and the size and depth of the excavation or construction site, like that. And also it is dependent on the thickness, stratification, or permeability of the geometry. That means how much thickness of the soil is present below the ground surface, and this soil is whether it is permeable or good permeable or not, like that. And required depth of the groundwater to be lower. Also, it is depend on the how much depth we want to require to lower the ground water table. Uh, these are for that if the we want to lower the groundwater to be much more depth, that then we use the dewatered system. If we want to lower the groundwater to be, or we want to remove the surface water, for that we use drainage technique. But if we want to remove or lower the groundwater to much lower depth or great depth, for that we use the dewatering technique. Also, we want to see or address the potential damage resulting from the failure of the dewatering technique. We know that if we extracted water from the ground, the void space is created because the excess pore water pressure is removed from the soil, and due to the overburden pressure, effective stress is increases. So there is a sudden ground subsidence is happen, or we can say sudden settlement is happen, which can damage the surrounding region or surrounding structure also. That may be need to in the mind when we apply the dewatering technique. Also, we can address we see the cost of installation and operation. We know that dewatering technique is most expensive than the drainage technique. If it is required to that only, if it is required, then only it is used. Otherwise, we can, if the small amount of water we need to address, then drainage technique may be incorporated. So here one chart is given, or we can say graph is given based on the we can say gradation graph is given based on the particle size or particle size distribution graph is given. Here we see that is some range is given from we can see that at the below first range is for gravel, second one is for sand, and third one is for silt and clay. For different region, for different ground dewatering technique is used. That means for gravel, that means that region, only cut-off drain or cut-off wall or barrier use. For that reason, while point is used, if the percentage of final is more, the gravity drainage is used, and furthermore, the theoretical limit higher gravity drainage is used. And for that reason, gravity drainage or oil point is used or electroosmosis is used. Like that way, by this chart, we can address or we can need when which technique is used. Need to use in our construction based on our particle size distribution. Moving to forward, another arrangement is given. It is based for permanent groundwater control. That means with permanently or permanent way we lower the groundwater table or maintain the groundwater table through some great depth. So for that reason, same one pumps are created and one pipe is inserted and water is collected from the surrounding soil and original water table is here. After that, the water table is lower like that up to that much depth and continuously the pumping system is uh, continuously the water is expel out or removed from this side through a pump and due to this continuous effect the groundwater table should be maintained up to a lower depth. So this another one is example is given is buoyancy effect of the underground structure. We know that that means we also say the uplift force effect or flow on underground structure. That means if we excavated one trench here and our structure is placed here, or we can say footing is placed here, and there is load from the footing, one load is, and another load uh, is created or is coming to this footing from this water. That means the original water table is here. Okay, original water table is here. So water is coming like that and created some pressure here. This pressure is nothing but uplift pressure. If the uplift pressure is more than our structure footing pressure or column pressure, then the structure may be failed. So we have to address or we have need to address this lack of arrangement. For that we need to lower the groundwater table. That means if we lower the groundwater table, hydrostatic pressure also reduce, and due to the reduced hydrostatic pressure, uplift pressure also reduce. So like that, the structure may be safe. That means structure pressure is greater than the uplift pressure. This is the stability condition. So another stability condition is the recharge groundwater to prevent the settlement. We know that for our construction site, we use sometimes the well pipes. So to use of this oil point, water table, the original water table is here. After this use of the these oil points, the for this construction site, the water table may reduce up to that level. But there is some influence of this lowering of the influence of this lowering of this water table up to a great distance like that. That means The original water table is here, and it will also reduce or influence or reduce uh, at that depth. Due to this reduction of this water table, suddenly the effective stress is increased. Due to this increase of effective stress, the settlement or the soil is compacted, a settlement is occur. If the settlement is occur, if there is present near present any structure is present, there may be collapse of the structure due to the sudden settlement. And to address this collapse, we need to recharge our oil point through oil point. We maintain the groundwater table. Sorry, we maintain the groundwater table for this reason. For that, we recharge the ground through oil point like the we dewatering through oil points. Like that also through oil points we recharge the ground and maintain the groundwater table like that up to that level to maintain the water pressure below that existing structure. If we maintain the existing pressure, there no need to settlement happen, so structure may be safe. So another example is given of deodorant. You can use the deodorant table technique for sand drain also. That means in slope, once sand drain is inserted, due to the sand drain, water is collected from the surrounding soil, and we know the sand is good for drainage purpose. And through a piping system or another arrangement, we can collect from water and remove the water from this ground surface. And another technique of the dewatering is this grout curtain or cut-off trenches around the excavation. We know that, or we can say that in excavation like that, the original water table is here. So we want to uh, lower the groundwater table below the excavation level like that. For this, we use the submersible or deep well in both sides. But to maintain the permanent, or you can say permanently maintain the groundwater table below the excavation level, there is barrier wall is created. This barrier is nothing but the ground curtain or cut-off trench. Due to this cut-off trench, the water cannot induce or water cannot insert it at this excavation level. So this may be safe from the surrounding soil. So this is one of the arrangement also we can use in our construction site. So now we discuss about the limitation and advantage and limitation of this deodorant technique. So deodorant system are easy to install and can eliminate the possible problems associated with the water during the excavation and permanent use. These are the advantage. This line is regarding to the advantage. That means it is easy to install and eliminate the possible problem associated with the water we already discussed, and also some limitation also for deodorant technique. We already discussed that deodorant may induce the ground subsidence. We know that if suddenly ground water is removed from the ground, the efficiency increase. Due to the efficiency, ground subsidence or settlements happen, and if there is any existing structure is present, adjacent structures, the structure may be collapsed due to the sudden settlement. So we need to address also by some research well points. And another technique also, another point is given here is that deodorant requires disposal or recycling of water removed from the ground and continuous power supply needed. That means deodorant technique we remove the groundwater and continuous power supply is also needed because these pumps are uh, uh, these pumps are uh, open or start close with current supply or power supply. So we maintain the power supply to continuously remove the water from the ground. So now there is two arrangement is here to oil points arrangement. One is single stage, another one is a double stage in both the side. In single stage, if we apply the drawdown curve should be like that. Okay, and for double or we can say if we apply the both side oil points, the drawdown curve is like that. So by that two arrangement we apply the oil points in the original field. So now we discuss about the sorry these two are discussed in the next slide. Please wait. So now we discuss about the uh, rate of water flow. Yeah, we can discuss about the permeability of the soil, which is needed, which is find out for this dewatering technique. If the more less permeability, the dewatering technique, another dewatering or high efficient dewatering technique is used. If the low permeability, the simple technique dewatering technique is used like that. So first of all, we need to find out the permeability of soil. So for that, we use the Darcy's law. It is nothing but the B is equal to Ki. K here it is the permeability, I is hydraulic gradient, and V is velocity of the water or flow of water. So here it is said this usually test soil very low permeability coefficient like less than 10 to the minus 9. It is suffix of this 10 10 to the minus 9 meter per second. So for that reason, so we need to first find out the permeability of the soil. So to use the in the real field condition. So first of all, we need to know the hydraulic gradient of the soil. Hydraulic gradient is nothing but the a drop of or loss of water during the travel, a drop of water during the travel, and length of water to travel. That means if the water table is here on water need to flow from here to here or another water table is here, there is some hydraulic drop or there is some head loss here. If there is no head loss, no need to, water may not or water is not flow from one point to another point. There need to be one head loss or one gradient. So water is flow from here to here. So it is del H. That much gap is del H, and the length of the water is flow from here to here is del L. So the hydraulic gradient is nothing but I is equal to del H, that is drop of water, and treated by del L. So here it is said that this hydraulic gradient is need to find out for finding out the permeability of the soil. So, but if to find out the testing purpose, we need high or hydraulic gradient. But there is some problem to use the high hydraulic gradient. The problem is that cracking in the soil or unrepresentative of the flow regime. That means Darcy law is not valid here. Internal erosion is happening or edge leak in test apparatus. That means cracking soil in the sense if the high hydraulic gradient is present due to the flow of water, crack may be developed. And due to the high hydraulic gradient, we know that the water when water flow from one point to another point, the water may be flow from some parabolic shape, some hyperbolic shape. so that may not flow from in a straight line. So the proportionality, that means V proportional to I, is uh, is not true here. So Darcy law is not valid here. So another is if high or increased hydraulic gradient present internal relation, that means due to the high hydraulic gradient, flow of water is very increased. Due to the increased flow of water, the surrounding soil, a fine particle may be eroded. So due to that, the internal erosion may happen. So like that, there is one table is given, which is uh, given for maximum hydraulic gradient use for the permeability is test. So for permeability, when the permeability is in between 10 to the power minus 3 to 10 to the minus 4 centimeter per second, the hydraulic gradient should be maximum hydraulic should be 2. And if like that way, if 10 to the minus 4 to 10 to the minus 5 permeability, then hydraulic should be 5. So like that way, for different permeability, different hydraulic gradient or maximum hydraulic gradient should be maintained. So now we find out the permeability in the field. So some field test. So here it one theoretical solution of water flow is given that the theoretical solution for water rate. So we need to find out the water rate. So the theoretical solution for water flow into the well with an unconfined and confined permeable layer can be derived based on the Darcy's law. Simplified models, that is Dupuit theme exposition for a sorry, few minutes. I am very thirsty now. I have to need water, so please wait few seconds. Sorry for that. Hello. Sorry for that. We discuss about the theoretical solution of water flow into the well. So here it is discussed that theoretical solution for rate of water flow into the well with an unconfined and confined permeable layer can be derived by Darcy's law. Simplified models, that is Dupuit theme approximation for a single well fully penetrating into the ground with the unconfined and confined permeable layers are used for this purpose. There are symmetrical problems with the oil in the center. So we need to find out now the water flow and also find out the permeability of the soil in the field condition. So for that we use the Darcy's law, and this Darcy's law is used by the Dupuit and theme for a single well system. And this technique is used for unconfined also and confined permeable layer also. Unconfined in the sense there is the soil is here is ground surface, and below this ground surface only permeable soil is present. No other soil is present. And unconfined is confined is in the sense is if there is ground surface is present up to some depth, one impermeable layer is present. After that, another permeable layer is present. After that, another impermeable layer is present. Like that, one permeable, one impermeable layer arrangement. This type of arrangement of the ground surface is called confined soil or permeable soil. So this technique is used for both the case unconfined also, confined also. And this to use this technique, one symmetrical well is used. That means one well point is here you use, and surrounding that, and based on this well point is center of this. surrounding soil. And up to that much of influence area, we need to find out the water flow rate and also permeability of the surrounding soil. So now if one by one for unconfined, confined soil, we need to find out one by one. So first we discuss the unconfined aquifer. So we see that one well is created here like that, and after that, which is penetrating up to here one point, it is given here fully penetrating in the ground. That means up to a impermeable layer we excavated or we excavated or created a one wall. After that, so we see that original groundwater table is here, and then if we apply the pump out the water from the surrounding soil through this oil, the groundwater table is slowly reducing and some uh, reducing and in oil point like that this water table is lowering. If we apply the pumping out from the water, if we apply the pumping out water from the oil, then this groundwater table is lowering. This groundwater, this line is original groundwater. After the pumping out, the line is nothing but called is periphetic line of level. It is nothing but drawdown curve. So for unconfined aquifer, this drawdown curve or periphetic line do not match with the level of the water level in the oil. So there is some gap. For to find out this gap, that is nothing but Hs, one empirical formula that is given. That is Hs is equal to C into Hw naught minus H naught whole square divided by Hw naught. Here Hw naught is original groundwater table and H naught is the groundwater table at the well, and C is some constant or factor which is nothing but here is 0.5. Now this well has some influence also, or that means there is at the surrounding soil when we apply the pumping out mechanism from this oil, the surrounding soil around the oil surrounding soil, grounded table of the surrounding soil also reduced. But after some distance, this uh, arrangement is reduces, or that means influence of the pump reduces. So this influence is nothing but we find out R. It's called R influence radius. We find out some empirical formula also. That means Ri is equal to C dash into HW naught minus HW1 into whole into root over k. Here C dash is some factor here also. It is that for multiple oil system it is 3000, and for single oil system it is 1500 to 2000 like that. And H naught HW naught is original groundwater table. Height of the original groundwater table. HW1 is H naught plus Hs. That means up to the prephatic line or drawdown line, the height. And K is permeability of the soil. Now we find out the permeability of the soil by Darcy's law. So for that, we imagine that one well is from the center of the well. Another well is inserted here from a distance of r from the original well, and the height of the water table of this well, which is distance about r, is h, or we can say z, and hydraulic gradient is d H by dz. Okay, or we can say dH by dr, hydraulic gradient. That means from here to here, the water is dropped, so there is one hydraulic gradient is created. Now we apply, and this imaginary well is created like that. If you in plane view, this R and this is much is height Z. So created one cylinder here. So and water is get collected at the surface of this cylinder like that, like that. If you see my drawing, like that here, here. So we need to find out the surface area of the cylinder and also find out the hydraulic gradient also. So after that we apply the Darcy's law. So we can see that the hydraulic gradient is here, it is del H by del R, and the area of this imaginary well is 2 pi RH. If you remember, the surface area of the cylinder is 2 pi RH. So we apply here. After that, so it is for small distance r. If we apply the Darcy's law, q is equal to AKI, and put all the values and apply for some range for H1 to H2 for a distance R1 to R2 and integrate it, we finally arrive some formula for find out the permeability for unconfined. You remember this formula is created for unconfined aquifer or unconfined soil. So like that we arrive this formula, which is K is equal to Q into Ln in R2 by R1 divided by pi into H2 square minus H1 square. So by this formula we find out the permeability of the soil. We know the flow rate by pumping arrangement. We know the distance from where to where we find this permeability. From R2 to R1, we need to find the permeability. So we know this distance. Also, some piezometer. We know the groundwater table below the ground surface. That means from R1, the groundwater table is H1. The height of the groundwater table is H1. For R2, the height of the groundwater table is H2. Like that. After that, we this arrangement we find out the permeability of this soil for unconfined equipment. Now we find out some arrangement or find out the influence radius by some arrangement, and this is given by Cosny for maximum influence radius. So Cosny is given that root over 12t by n, and in this root over also another root over it is given there qk by pi, where t is the time of this pumping out, n is porosity of the soil, and k and q is permeability and rate of flow of the water, and pi is constant, we know that. So like that we find out the influence radius, that means up to what distance this pumping is influence the area, influence the surrounding soil. So now we rearrange some, or we if we rearrange the formula for the influence radius and the oil radius, we find out the permeability like that. That means for H1 we we write here the H naught, that is the groundwater table of the well. For H2, we write here the capital H, that was original groundwater table. And R is the influence radius, and R naught is the radius of the well. So by that arrangement also we can find out the permeability of the soil. So after that we also find out the depth of the water table for some distance r. For that also we need to arrange this formula like that, and we find out easily the depth of the water table for that region only. Moving to forward, now we need to find out the permeability of the confined aquifer. We know that in confined aquifer, here is the ground surface, one impermeable layer is here, after that one permeable layer is here, after that another impermeable layer is there. So we know that the water only flow from permeable layer. That means water is present here only. And if we apply one piezometric instrument, we by this instrument we need to come out that the groundwater table for this permeable layer, height of the groundwater table for this permeable layer is up to that much depth due to the pressure of the overburden pressure. So if we apply, and we can see that the drawdown curve is connected or meet with the level of the water level of the well, which is not in the case of the unconfined aquifer. So same Darcy's law is applied to find out this permeability in case of aquifer. But if you see that the water is only come to this well from this region only. If you see the drawing I draw online, only that region the water is come to this well only. So the height of the arbitrary well is fixed, that is HDR. So now if you say all the arrangement is fixed here, only change is the capital H. It is nothing but the height of the permeable layer that is fixed. So after the applying the Darcy's law and for some arbitrary distance R1 to R2 and some arbitrary water table H1 to H2, we get like that formula for the confined aquifer permeability formula, that is Q into L log ln log R2 by R1 and 2 pi H2 minus H1, because we know that H is the uh, depth of the permeable layer, and which is also constant or fixed for a confined aquifer. So the final formula is like that. So we already discussed this slide that the drawdown the two different way we can draw down the groundwater. One is if we apply the one side of the excavation, and other is we apply the both of the side of the excavation. So like this arrangement, the groundwater for if we apply both sides, the groundwater table is draw down like that. If we apply one side, the groundwater table is lowering like that. And if also we apply the mass system, we already discussed all these points. And now the multi-well points, that means if we apply this, we previously we discussed for the unconfined aquifer and confined aquifer for a single well point. If we apply this uh, formula for multi-well points, that means here, 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 and need to find out the how much water is required to pump out for this region. This arrangement is created for an unconfined aquifer. That means here x1, x2, xn dot 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 xn is nothing but the distance from this particular point, and we need to find out the water flow or rate of water from this particular point, and apply this unconfined aquifer formula by some little modification. And the Z is the nothing but the depth of water for this well point. And this is arrangement is given by the Forchnier in 1930. And by this arrangement, we need to find out the rate of water flow for different oil points and like that this formula or arrangement. If we arrange this oil point in a circular shape, like in the next slide, if you see that, we use this formula to find out the water flow for that P point, where AW is the radius of the this arrangement of the oil point. So here it is one conclusion is given for this regarding the dewatering techniques to find out the permeability, that is unconfined confined. That means we use this formula for fully penetrating oils. That means we consider that the oil is created up to a hard stator mode. But in the real scenario, it is not like that. That means oil is created up to a certain depth, no, not penetrated to a hard stator. So for that, we need to correct or we need to arrange something or correction something needed. So which is based on the field experiment or field trial test also. So now in the last slide or last day, we now try to solve some problem, which is very simple in this. And this problem also we find out in the book which is written by J. Ham, which is a book for ground improvement techniques. And most of the slides are taken from that book only. And one problem is given, and now we try to solve this problem, which is which is regarding the dewatering technique of the unconfined aquifer. So here it is said that a job site required an excavation of a rectangular area, which is a plain area is given 20 meter by 170 meter. 170 meter. Uh, Sorry, it is right few seconds. Sorry for that. Um, so it is said that to a depth of a job site requires an excavation of a rectangular area 220 meter by 170 meter to a depth of 15 meter, as shown in figure. Or we should see the figure in few minutes. Few seconds. The existing groundwater table is at 5 meter depth, and below the ground surface is 30 meter thick gravel with the permeability of 5 into 10 to the minus 5 meter per second, which is underlined by bedrock. The groundwater table should be lowered to 1.5 meter below the bottom of the excavation. Deep wells are used to dewater the site. Calculate the total required discharge if the 200 diameter deep wells are used. How many deep wells are required? So these are our problem. So now we try to solve this problem based on the formula which is I discussed in previous slide for the unconfined equipment. So here the figure is given. Sorry, here is figure is given. Is there is this is plane section and this is uh, the cross sectional view. So in plane section it is given that the one excavation is created for the site is created or prepared, which is 250. Sorry, which is 250. So 220 meter by one uh, Sorry. Sorry, I have. Sorry for that. Sorry for that. I have some network issue here. I'm again sharing my slide. Please wait. So now we can again join here. So we're discussing about the uh, this problem. The plan area we need to excavate this up to this plan area up to a depth of 15 meter. But the groundwater table should be below at point 1.5 meter below the excavation level. So here the plan area is given 220 meter to 220 meter to 150 meter. But our formula is created for a circular well. So we need to convert this rectangular plane area into a circular one. So for that we need one equivalent circular area. So we need to convert this area for equivalent circle. So for we now we moving to the solution part. So for equivalent surface, we find out by this formula. So the equivalent radius for this excavation is find out with is nothing but this pi r square is equal to L into B. So we convert this rectangular arrangement into a circular one. After that, we apply this formula of this unconstrained equation. So in this second, we need to find out the height of the water table, or uh, we need know that in uh, original groundwater table is up to from here to here. That means 30 minus 5 meter. That is 25 meter. But we need to keep our groundwater table below the foundation excavation level for up to 1.5 meter. That means after the pumping out, the groundwater should be level should be like that. For that, it is 30 minus 1.5 minus 15 meter, which is coming out 13.5 meter. That means up to that much depth of the ground we need to maintain our groundwater table. So we already find out the HW1, also find out the HW0. Now we find out the influence area. That means for that much of permeability and for that much of pumping out test, up to what distance this pumping out test is influence the surrounding soil. For that, we need to find out the influence radius. For we know that to find out the influence radius, we use the empirical formula, one empirical formula, that is Ri is equal to, which is influence radius, equal to C dash into HW naught minus HW1 into root over K, where C dash is here is given 300 3000, and H naught is here we find out 25, HW1 also find out 13.5, and permeability is given here is 5 into 10 to the minus 5. So after this we find out the influence radius. So after finding the influence radius, we find out the rate of flow for that pumping out test for one excavation of this excavation. To find out this rate of flow, we need the unconfined aquifer formula because here the all the arrangement is given for the unconfined aquifer, or you can say unconfined permeable soil. So after all the values we already find out and put all the values in this formula, we already find out the rate of flow is required for to maintain this 13.5 meter height of the well, height of the groundwater table after the pumping test. And for that, now we find out the number of well point required. For that, uh, uh, to excavate the 0.0864 rate of groundwater flow rate maintained. So here it is given that the for one well point, the radius of the well point is given is diameter of well point is given is 200 mm. And so the radius is 100 mm, and if you convert it this radius into meter, it is zero point 0.1 meter. So for this one, first we find out the rate of flow for one well point by this formula again for HW1, or we can say R1. We put the R naught is zero point 0.1 meter. For after that we find out for rate of flow for one well point. Now if we divide the total well discharge or rate of flow by the one well point discharge, we find out the number of well point required for this particular site. And here it is comes out 10 well point is required for this problem. So here it is. This is the solution of this problem, which is given here, and I am already shared this slide also, and also this solution also, and also the video also recording also we will share. Now the next another aspect is given, which is last one is here. Up to few is remaining. Here it is given that we maintain the stability during the dewatering. To maintain the stability, we need to address or remember that overburden pressure of this excavation should be greater than the uplift pressure of the soil. Uplift pressure is coming from the water table depth. If the high water table depth, high uplift pressure is created. So due to the uplift pressure, the bottom of the excavation is burst or damaged. So we have to arrange in such a way that the overburden pressure of the above the excavation should be higher than the uplift pressure, because if it is less, the below surface of the excavation should be burst or damaged, and which may which creates some detrimental effect during the construction site. So we have to maintain the this arrangement, that is uplift pressure should be less than, or we can say the uh, overburden pressure should be greater than or higher than the uplift pressure. To maintain this, we need to lower down the groundwater table. For that, we need the dewatering technique, which is already discussed here. So last one in this session, we maintain the stability also in the adjacent structure also. To maintain the stability of the adjacent structure, we need to discharge uh, the adjacent soil through the some research oil, because if we reduce during our construction, we need to reduce our groundwater table. Due to the reducing the groundwater table, there is some influence of the surrounding soil also. The surrounding groundwater soil groundwater table also reduced. Due to some reduction, effective stress is increased. Due to this effective stress, settlement is occur. We know this consolidation settlement is occur when the increase of the efficiency happen, and by this formula we find out the settlement. And to maintain to address this settlement, we maintain the water table of the surrounding soil, and for that we need to recharge the oil. To find out the recharge, the quantity of the pressure of the recharge oil, we need to find out this. Sorry, we need to find out by this arrangement. We need to find out the how much effective stress will increase when the groundwater is lowered down, and for certain settlement. And to find out the excess, effective stress, we find out how much water is required to maintain or to address this excess or effective stress. So like that, we find out the how much water is required to recharge this oil plant. So it is all about the drainage and dewatering technique of one of the groundwater technique. So here now we will stop our session. I will share this presentation through Google Drive. Also share some few problems and previous assignment problem solution. You can go through it, which is help you to solve the assignment problem of this year. Also, we record this session. I recorded this session, and I will share this recorded video to you through YouTube channel, and this all these details will be shared by the NPTEL team. No need to worry. And now we will stop our session here, and wish you happy weekend. And we can meet again in the next week, which is week 7. And in this week, we're discussing about the preloading vertical drains again, which is another in details, which is another ground improvement technique. And now we stop here. It is already 8:10, so we stop here. I am leaving the session. Thank you very much. Thank you all.